So now let's look at the Bose-Einstein statistics. So the rest of this class will be dedicated to looking at the various limits of Bose-Einstein statistics, okay? And in particular, we will derive how, the case where at low temperature, a lot of particles, there's a like a critical temperature, and then how a lot of the particle go, and then they can occupy the lowest energy state. Okay, so now before we do that, let's just just review a very simple fact. And the simple fact is that, if you look at the expectation value of the number of particles, then that's going to be the sum of the expectation value of the number of particles at each energy state, right? And that's given by this expression. Now, what is Z? Small z is introduced for notational purposes, and it's defined to be e to the power beta mu. And this has a name. It's called the Fugacity. So if you look at this expression, we see that, well, for that mu must always, sorry, I wrote something wrong here, because this should be Z inverse. Let me see. Yeah, it should be Z inverse. Yeah. So the idea is that mu must always be below E, especially it should be always below the lowest energy state, right? Because if mu were to approach E0, what will happen is that N0 will blow up. And that means that the number of particles in the lowest energy state will be infinite, which is not a physical thing. And therefore, for this formula to make sense, the mu is good, always will have to be less than epsilon E naught. And we can choose we can choose to count our energy levels in such a way that we can set E naught to be 0. If that is the case, then the chemical potential for the boson must always be negative. Okay, so what does that mean for the fugacity? That means that the upper limit of fugacity is going to be 1, right? So with that in mind, let's go and calculate what N is for a Bose gas. So what is N? So N is 1 over beta d log of Z, where Z is a partition function, d of mu. Right? So this is, now if I'm looking at a non-relativistic Bose gas, or gas of bosons, then this is going to be, well, in principle, this sum is 1 over Z e to the power beta e of I minus 1. But we worked out what this sum is in the continuum limit, and that's going to be dE, and the density of states, GE. So this is basically what becomes of the sum. And then we have, multiplying that, Z inverse e to the power BE minus 1. And for non-relativistic ideal gas, G was proportional to square root of E. Okay. So, before we jump into the various limits of the Bose-Einstein statistics, let's derive the equation of state, or let's try to derive the equation of state for the ideal Bose gas. So we're looking at the ideal Bose gas, and let's try to work out what its equation of state is. Now, since we are working in the grand canonical ensemble, if I take the grand partition function and take its logarithm divided by beta, we know that that is going to be P times V. Remember, that was the nice thing about the grand canonical potential. That the grand canonical potential, is proportional to V. So we can, now what is log of Z? Now log of Z is minus sum over states I, log of 1 minus E beta mu minus EI. This is the Bose statistics, the partition function. But for our case, this sum is this integral, and the density function G of E was V over 4 pi squared 2mh squared, the whole thing in 3 halves, square root of E. This is for the non-relativistic particle in a box. That's something we derived. So then PV is going to be minus 1 over beta, the integral from 0 to infinity of d of E, G of E, this function that I just wrote, times log of 1 minus Z e to the power minus beta E. Okay? Is that clear? Right. So now we can do a bit of a manipulation. And the first manipulation is that d of dE of e to the power 3 halves times log of 1 minus zeta e to the power minus beta of E. If you do this, then the first term is 3 halves of square root of E log of 1 minus zeta, well, it's Z. Yeah, I'm writing this Z because it's a small z, fugacity, minus B of E. So this you will recognize as this integrand up to stuff, and then there will be another term, and the term is plus E 3 halves Z, and then beta E to the power minus beta E. This beta comes down because of the derivative acting on the exponential, and in the denominator we have 1 minus Z e to the minus BE, right? So the thing is that this thing is a total derivative, and it's you can show that it actually is 0 in both limits, and therefore the integral over this factor drops out. So what we can do is that we can replace, this guy, which is here, by minus of this guy. So we can write PV as 2/3 integral over E G of E divided by Z inverse EBE minus 1 DE. Now, what is this thing? This thing is nothing but the expectation value of energy E. So we can write this as 2/3 of E. And using a notational sloppiness that physicists are well known for, we can just write this as E. And this is implicitly the equation of state. So this is implicitly the equation of state. I say implicitly because, usually in an equation of state, we expect an explicit dependence on T, an explicit dependence on N, but none of it is there on the right-hand side.